Hey everyone, my name is David Hull, and I'm here presenting my findings from Lab 3, Black Hole and Orbits in Physics 2211. So let's jump in. I'll start with a quick introduction. There are two parts of this lab. Part 1, the goal is to find the mass of the black hole, and we do this by analyzing the motion of a star that was given to us in the starter code. The second part, you're an astronaut that landed on a moon of a planet and decided that you want to orbit the moon and planet in a figure-8 pattern without crashing into either the planet or the moon. Also, this lab is used to demonstrate Newton's second law and its relationship with momentum. So let's get started with part 1, the black hole. Things to consider here. Newton's second law, which states that the net force on a system is equal to the change in momentum over the change in time. Since the change in time is very small, we choose to consider the derivative of the momentum. If we expand this equation, we can find the parallel and perpendicular forces of momentum. And then in this case, the star is the system and the black hole is the surroundings. It's also very important to this lab. The force between them is the gravitational force, which we know is equal to g times m1 times m2 over r squared times p hat, as you can see on the right. When we rearrange this equation at the bottom right, we can see that when we set everything equal to m2, which will be the case for this lab, we can solve for the mass of the black hole. So yeah. Alright, so looking at the glow strip from part 1, the mass of the star was given to us, and then in order to get an accurate measurement for the mass of the black hole, we will look at how the momentum of the star is changing at different times during its orbit in the black hole. So at the top, you can see the initial conditions of the model, and the next section shows how the velocity components will be calculated at the timestamps, and this code was given to us. So here are the next computational steps I did to find the parallel and perpendicular components of the momentum. This will help us find the net force acting on our system, which is the star. And then if you look at line 190, that is very important. This line calculates the mass of the black hole at all given time increments by using the change of momentum over the time formula. It uses the change of momentum over time formula times the distance squared over gm. Which, if you remember, this is the equation that we derived early in the video that I said would be important. Here are my results from part 1. The average of all the masses produced from the code was 6.09 times 10 to the 43rd power. We took the average because since the orbit is not perfectly circular, the mass will be slightly different at all of the different timestamps. Here is pictures for the visual representation of the net force, perpendicular force, parallel force that is acting on the star. You can see that the orange is the net force, the cyan is the perpendicular, and the small pink one, it's very small, is the parallel force. Alright, so getting to part 2, and just to restate what we are trying to do, we want to find the initial velocity of the spaceship so that it does not crash into the moon or planet while going in a figure-8 pattern. Here are some of the initial conditions I entered for this code, and note that the initial conditions for the moon were given to us, and for the initial velocity of the spaceship, once we finish our code, it was just a whole lot of guess and check. Here's another big chunk of code, but all we're doing is basically isolating our system and finding all the external forces acting on it. In that top chunk of the code, we are calculating net force acting on the moon by using universal gravitational formula, which you can see we use a lot here. The next section is using the ship as the system and finding the net force acting on it. We did this to find the motion of both systems over time, which is why we need the position and velocity update formulas you see at the bottom. Here are the results. So after many attempts, I found a velocity that made it so that the spaceship does not collide with anything. However, as you can see, it is very not figure-8. But the instructions specify that the figure-8 may be impossible, so this is good enough. Next, I'll discuss a few possible errors. This is a simulation, so the results don't really reflect what would actually happen in reality, considering that it's assuming that there are no outside forces acting on the system. And then also, our accuracy may be off. Put this on there because we did a lot of guess and check, and I'm assuming there's better ways to find the values that we use for velocity and stuff like that. Lastly, we will do the discussion section of the lab. So what does it mean? It says to discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So earlier we showed that mathematically net force is equal to the rate of change of momentum. However, net force is much harder to calculate since you would need to know every force acting on the system. Rate of change of momentum, on the other hand, you only need to know the system's change of motion, which is why we use it in this lab. What if this is an imaginary system that has a black hole, a star, a planet, and a moon? And then if we wanted to predict the motion of the entire system, what would you need to include in this model? Basically, I think that it's very similar to our lab. If this was our system, then to predict the motion of the system as a whole, all you need to include is the masses, positions, and velocities of each the black hole, star, planet, and moon, along with the gravitational forces between each one of them, which would take a while to compute, but it's similar to what we did in this lab. That is all I have. Thank you all very much, and have a nice day.